We are the Solar District Cup team 2022. We are the team representing Rose-Hulman. With us today, we have Patrick, Kaylee, Rebecca, Ben, John, and Luke and Shane. Ben and Shane will be available for questions, and the other five will be presenting.
Starting off, we have our team's competition approach. Here we have this diagram showing how we divvied up the work for the various documents. This was included in our files that we submitted, and we'll get right into it.
So our team was assigned the Ohio State University as our district use case. Within this case, we've been working on two separate sites. The first is the Wexner Medical Center, where we have been designing a solar plus storage system that will provide power to critical loads during outages and also provide resilience to the overall system. When not performing these tasks, the site will also be used for economic use cases such as peak shaving and load shifting. More on these later. And then the second site will be a piece of pasture land also owned by the Ohio State University. This will be known as an agrivoltaic site. This land will be developed for the purpose of selling power back to the grid while minimizing environmental impact.
So these are our overall electrical system designs for both of the sites. For the medical site, we split it into two designs, one for each of the solar array systems located on the buildings, and then one for the solar array systems located on the parking garages. So the goal of the solar array systems on the buildings is to tie back into themselves and produce a part of their energy consumption. The goal of the solar arrays on the parking garages is to power the battery storage system, whose power we use to power the three essential buildings at 50% load in the event of a power outage. More on this later.
Here's a color-coded map of the medical center. Each building has been colored according to its viability as a platform for solar installations. Green buildings are deemed to be ideal due to factors such as roof size and lack of proximity to other tall buildings. Yellow buildings are considered not ideal, but were ultimately used in order to increase the total power we generated. Blue structures are parking garages and were used in conjunction with canopy mounts for panels. And then lastly, red buildings were deemed as unsuitable for solar panel installation due to either small size, cluttered roofs, or proximity to helipads.
Oh, okay. As a team, we came up with 5 options for the solar panel placement on the agrivoltaic site. Our civil engineering team then completed a geological survey analysis to determine the best location for the placement and construction of the solar panel installations by utilizing the USGS web soil survey to analyze the site conditions at each point to balance the ideal soil conditions, sun availability, drainage and erosion potential, and existing site utilization as a grazing land, ultimately choosing point 2.
During normal operation, the power generated by each building on the medical site will be used to power that building. This means that in practice, these buildings do not need meters since the inverters can tie in behind the meter. And though we were not given consumption data for every building on the medical site, the percentage offset for buildings that we were given consumption data for and installed panels on is shown here. As you can see in the highlighted data, we produce significantly more than the 1% power offset requirement is given by the competition for each of these buildings.
Here we have the diagram that we saw earlier. This is just a way of us highlighting that the solar panels are connecting into inverters on top of the parking garages at the medical site. And those then go into a metering system that we'll cover, and then into the existing distribution grid, of course. And then we also have charge controllers that we will talk about next. With more metering and the interconnected systems, this again just highlights that there will be a meter on each building. So we accounted for that in our budgeting, and this is our connection.
So then the metering systems will feed into the existing distribution systems, and then next slide, please. They will go to a charge controller. So the role of the charge controller is to determine if the batteries are fully charged and ready to be used in the event of a power outage. So if the batteries are full, the energy created by the solar panel systems on the parking garages will go to contributing power to the essential buildings just under normal circumstances. You'll also notice that throughout the system, we have had a variety of rectifiers and charge controllers and inverters in order to control the current to AC or DC, depending on what is needed at any given stage.
So then for the batteries here, the batteries had to provide power for a 3-hour outage. Average time about for a power outage, according to Energy Information Administration, is about 2 hours. So the total capacity for all three critical buildings, the Harding Hospital, Davis Heart and Lung Institute, and the Wexner Medical Center building, it's about 6.6 megawatt hours for all three, and our proposed array has satisfied that requirement.
Here we have the agrivoltaic site. This is the panel layout that we did in Aurora Solar to be testing and verifying how much energy we'd be producing. On the right there is the one-line diagram, or part of the one-line diagram, that is output by Aurora Solar. And we ended up with a final production for just this site of 168 megawatt hours. And then next we have distribution system. Overall, yes, here's the production for the medical site by building, the number of panels, as well as how much each one produced, with our results at the bottom of everything totaled. And then the next slide is again the agrivoltaic site with 400 panels and the overall energy produced for that site.
So then for the resilience analysis, we ran a simulation to determine if the necessary battery storage was to survive a blackout at any given time. And after running all the simulations at various points of the day, we have found that our solar panel arrays have been able to satisfy that requirement of the competition. So then for the next part with the peak shaving and load shifting, we decided to discharge the batteries at the peak consumption of the day, usually about 10 a.m. to 2 p.m. For buildings. And we ran calculations and got an estimate of about 20% of offsetting the peak consumption by the critical buildings by each day.
Now on to the financial performance. Since we have two distinct photovoltaic systems on separate sites, we made two separate financial models. Shown here are some of the data from our medical site model. The blue arrow shows the site's IRR, which falls within the 9 to 11% requirement as given by the competition. The green arrow shows our price per kilowatt hour, which we were able to get down to 6.5 cents. And lastly, the black arrow shows the total expected development cost of this project, which is $7.44 million. Since we're incorporating both a construction loan and a MACRS federal tax incentive program into our model, the cost to investors will be significantly reduced. In the same format as the previous slide, this covers a high-level interpretation of our agrivoltaic site financial model. The blue arrow shows the site's IRR, which once again falls within the 9 to 11% requirement. The green arrow shows our price per kilowatt hour, which is 10 cents in this case. And the black arrow shows the expected aggregate project cost, which comes out to be $262.6 thousand. Once again, on the agrivoltaic site, we are incorporating both a construction loan and the MACRS tax incentive program in order to reduce the cost passed on to investors. Pictured here are the payback times for each of our projects. On the left is the medical site, which is estimated to break even at 9 years. And then on the right is the agrivoltaic site, which is projected to break even at 8.5 years. Note that both of these projects will pay for themselves significantly before the end of their projected 20-year lifetime. And then finally, shown here is the net present value, or NPV, of each of our sites. With the medical site is on the left at $8.5 billion, and the agrivoltaic site is on the right at $98.7 thousand. Note that both of these values are positive. This means that the value of the positive cash inflows or revenue is greater than the cash outflows or costs associated with each of these projects. Therefore, these values indicate that these projects would be a good, worthwhile investment for investors.
All right, now moving on to our development plans and starting with the urban district. So for the structural design, our team found it important to design the supporting infrastructure system in a way that allows for the panels to withstand various types of loads such as wind, snow, live, and dead loads. Our team also ensured that the added weight from the panels and supporting system can be supported by the existing structures. For our design, we use HSS steel members to support the weight of the panels and base plates with anchor bolts to attach the panels to the roof. All designs were completed according to ASCE 7-16, along with the Ohio State Building Code. Our construction schedule was developed using RS Means construction manual to help determine an estimated construction schedule for the installation. So we would begin the construction during the summer months to minimize impacts to student life during the main staging periods, and estimate the installation for the urban district would take around 8 months to fully complete. And in order to meet the complicated staging requirements with the urban district installation, we will utilize paved parking surfaces to prevent any blocking any pedestrian walkways or staging on any existing grass surfaces that would then require remediation efforts later on. By performing installation during the summer months, we anticipate minimal impacts on commuters by utilizing paved surfaces, highlighted in orange, and staging highlighted in red. Nearby each building that will be having solar panel installations occur. This will allow the installations to be expedited rather than having a single central staging location. And moving on to the Pastureland. So similar to our urban district, the Pastureland site, we also had to consider our structural codes at play here, most specifically with wind loads on this site. But we also had to make sure we took in consideration the soil types and foundations that would be needed to ensure the solar panels were securely anchored to the ground surface. To do this, we will utilize a concrete shallow foundation, and we would also make sure these all complied with ASCE 7-16 along with Ohio building codes. Additionally, we consider the current use of the site and the design of the panels to elevate them 7 feet to allow for existing uses of the site to continue without hindrance. Additionally, on the Pastureland site, one of the unique things that we had to manage is stormwater management. So in order to meet the evolving regulatory requirements surrounding stormwater management for solar panels, we have utilized guidance from states with some of the most conservative state requirements in regard to stormwater management to ensure our design would remain applicable in Ohio, even if implementation is a few years out. To do this, we'll utilize an infiltration trench that will have a gravel filter to encourage sheet flow and prevent erosion from the concentrated flow coming off of the solar panel drip edges. The filter has been designed to be wide enough to accommodate a predetermined selection of solar panel angles and allows for water to naturally infiltrate during normal rainfall events with a conveyance structure for excessive rainfalls. Looking at the profile view of this infiltration trench, you can see that the perforated pipe that will run along the length of the trench, and excess rain flows could then be conveyed into the nearby stream bed and into the local watershed. Our construction schedule for the Pastureland site, we also use RS Means construction manual to determine these. This would also occur during the summer months to utilize hopefully decent weather conditions that the winter and spring months could not be as good. And the construction on the Pastureland site is estimated to take around 3 months total for implementation. In our construction staging for this site, there is a unique consideration here because we don't want to have equipment traversing the Pastureland because that could create bare spots and potential erosion. Utilizing a existing gravel roadway to the west of the site, we can have a central staging location on the northwest portion of the site and have minimal impacts of equipment traversing the Pastureland or have to remove existing fence lines.
So moving into our analysis methods, we completed an analysis that would allow us to verify the performance of our chosen tilt angle using Aurora Solar. The tilt angle that we chose for our solar panels was 0 degrees, so we wanted to verify that this was a good choice by looking at the system losses due to the tilt angle for every building in the medical site. A goal that we set for our systems was that none of the buildings would have a system loss due to the tilt angle that was greater than 20%, and we are happy to report that we exceeded that goal with an average of 12.08% of the system losses being from the chosen tilt angle for the entire medical site. Similarly, we also completed an analysis to verify the performance of the inverter that we chose. So we set a goal that the system losses due to DC to AC conversion was less than 2% for each building of the medical site. We again met that goal and found that on average, the system losses due to inverters was 1.58%. And then moving into our technology selection, in order to choose our solar panel type, we compared 3 standard types of solar panels, as you can see here. We ultimately chose the PERC monocrystalline panel for its low cost and high efficiency, which is a standard monocrystalline solar panel with a passive layer added to it that helps increase efficiency.
Rebecca, I am so sorry to interrupt. We are at time.